So if we look at this, we're going to look at this part here. Okay, we have the sum where I is not equal to j. All right, so we have AI, bj, EI, wedge, EJ, and then we can look at this as a sum where I is less than j to the n, and we see we get this, and this we can see is similar as the determinant. So we can say that this thing has, not the determinant, but the whole thing has n choose 2 terms. So that means that this sum has that many terms. A general blade, so we can take this now and we further generalize this. So now we can say x sub k, and we do it now to n, and here we have the determinant where we have I sub 1 and c less than, okay, and then we similarly, and we end up with n choose s terms. So it should be noted that that's the number of terms, not the number of entries into the determinant. Okay, and of course, x's must be linearly independent, otherwise all determinants are 0. The interaction of cliffs. There are 2 ways in which cliffs can interact. One is addition subtraction, the other is multiplication division. To make cliffs into an algebra, we need an associative multiplication distributed over addition. We shall define the associative multiplication first over the basis, vectors, then over all vectors, and finally over all cliffs. So we will develop this. Okay. Now, this is the relationship, okay, and the transition between Grassmann's way of looking at things and Clifford's way of looking at things. So we choose a basis of linearly independent vectors, E1, E2, etc., where n is 2n, where n is the dimension of physical space. Okay, and the Grassmann product we define here as the wedge EI, wedge EJ is free except for the constraints. So where in Grassmann system we have EI wedge EI is equal to 0, and EI wedge EJ is anti-symmetric, where we have negative EJ wedge EI if I is not equal to j. But in Clifford's we have slightly different constraints, where EII is equal to 1, and EIJ, well, that's also like Grassmann's anti-symmetric. Both products are extended by associativity to E1, EI1 all the way to EI, okay, wedge, and this is Clifford's way of looking at the same thing. So in the case where EI1 to EIS are all distinct, both expressions in 3 are free except for the constraint that they are totally antisymmetric under permutations 1 to s. Therefore, the product, so if we look at it in terms of Grassmann's way of writing it and Clifford's way of writing it, can be identified if I1 to IS are all distinct, and in this case, it's called a simple blade. Blade, by the way, is Clifford's term. If all the factors are all distinct, the Grassmann product vanishes, but the Clifford product is non-zero and homogeneous with grade equal to the number of factors that appear an odd number of times. So, if, for example, as we say with Clifford's system, remember, if he's an EI is equal to 1, so if we look at this here, we can see this will collapse to 1, this will collapse to 1, so we're left with E1, E2, and this has a grade of 2. But if we have a situation here, E1, 1, E2, 2, E3, 3, this collapses to 1, to 1, to 1, and the grade becomes 0. Okay, multiplication of blades. So in this case, things are getting a bit more complicated. So in this case, we had to condense the language and make it a little bit simpler. So we're going to say A is equal to this, okay, and B is equal to the bracket this, the wedge, and the Clifford, okay, is the Clifford product. So we have now a double sum, this, okay, with this. Okay, and these represent the determinants that I was talking about earlier, all right? And so So when we talk about the sum, that sum we mean as before, we have these I1 less than I2 less than I3, and similarly for J, and so that's what it means. So, and of course, as I said, these A, the determinant A to the R represents this determinant and that determinant, so we don't have to keep on writing these things out over and over and over again. Okay, and then here we have E, Ri means these elements, and here to means there to the JK. Oh, and I forgot. Is anyone timing me? I forgot to time myself.
What time are you supposed to finish at?
5:15.
Okay, so
5:05.
okay, I got a little bit, so I apologize. Okay, so in the sequence I, so we have, when we call I sub 1, I sub R, and J, I sub 1 sub. We have these pairs. Now the thing is about pairs, we want to look for what's called the matching pairs. As I showed earlier, those matching pairs, those are the ones that are going to collapse to 1. And that's very, very important when working with using Clifford's system. So by removing the matching pairs to a simple blade, R plus S minus 2n. So the minus 2n are each matching pair that comes up. So we're going to subtract off each matching pair. Hence, we can write now AB, which was back in our condensed language, and then we just, until we finish using up all the matching pairs. Okay, in terms of this, so finally we get this is just the total contribution of 5, this, okay, in terms of the sequences of I and J, and which is of matching pairs. So writing 7, okay, so we're going to look at 7 now, so we can rewrite 7 as the AB, the sum, okay, sum of from m to 0 to m to the maximum number of matching pairs. So we're matching off as many matching pairs as we can. And remember, we have, when we turn them around to get them to connect with each other, they'll change signs. So that means, for example, when we have m matching pairs, well, that will be the minimum RS. And the reason why the minimum RS, because if we only have R, if R is less than S, that means at most we can only have R number of matching pairs. So the last term must be as follows. So since any two homogeneous objects, A of grade R and B of grade S are the sum of blades of the same grade, we obtain the associative product by the distributive law. Now, by expressing any pairs of cliffs as a pair of sum of homogeneous objects, the associative product of any two cliffs is determined by the distributive law. So, the vector space CLN consists of all cliffs has now been promoted to a graded algebra by defining the associative product. So here we go back to our condensed language, and we rewrite 8, okay, and this is from n0 to n, where we said is the minimum, because we only have so many that we can match up with, or possible ones, so we end up with the bracket AB, R plus S minus 2, which is actually seen in the geometric algebra that I was studying by Hestenes. Since AB, R plus S minus 1 consists of the sum of all terms in 5, which is what we looked at earlier, and the sequence, we have I1 and I of n matches. So that's really what we're always looking for, is looking for how we can get these matches. So we take, again, using that condensed language, each factor, and we pass through. So we either, to get those two connected, like the E11s, so we can collapse them. And sometimes we have to switch things around when we're passing through. And that's how we get the following formula. So because we have -1 to the m, -1 to the rs, and etc. So the relation holds for every term contributing. So here we have this relation holds for every term contributing AB, r plus s minus 2n, such AB is equal to r plus s minus 2n, and here the rest of the formula. Okay, by linearity, 10 holds, meaning this formula holds, for any homogeneous cliff AB, not only for blades. So this holds for all homogeneous cliffs. Okay, commutative relations on two cliffs. Now let AB be any two cliffs. Each can be resolved by into graded parts. So here we have the two graded parts. Okay, for each RS, we proceed as earlier to derive the commutative rule, and here we go. And this is the formula that Hestenes showed in his book on the geometric algebra, the calculus of geometric algebras. Okay, so here we have the two, all right, and we continue the cliffs over the outer product. AR and BS is defined in the first term for n is equal to 0. So if we have no matches, this is what happens. That's the situation with no matches, and that would be similar to what would happen with Grassmanns. So homogeneous cliffs, the linearity of the two outer products of any two cliffs. So for m is equal to 0, as I said, no matches, and we get, and this would agree with Grassmann's definition. Now, so then if we continue, now if R and S is, if RS is even, if either R or S is even. Hence, both Grassmann, again, for both Grassmann and Clifford. So the outer product of two blades, Clifford's words, and Grassmann's idea was using multivectors, is antisymmetric if both grades are odd, otherwise it is symmetric. All the above reasoning is easily extended to the outer product of any two homogeneous cliffs and linearity of any two cliffs. Okay, so how do we get Quaternion? Okay, how do we get Quaternions from Clifford algebras? Well, simple example. Well, we do know that I, J, and K do not have the same behavior as E1, E2, E3. So we have to define using the bivectors of E, I, J, and K. So for example, I is equal, so always is equal to negative E2, E3, J is equal to negative E3, E1, K is equal to negative E1, E2. So then we just plug in for I squared, and we just plug it in, and then we just do the collapsing as before, and we see here we have, okay, we have to, okay, switch it around, and by switching it around, we change the sign, but then we can now collapse these two, the two 2's, and then we end up with the negative 3 3's and negative 1 as expected. And similarly, we can do for ij squared, ik squared, and ik squared. So now, and then of course with ijk, we just plug it in, and again, we just collapse there 3 3, 1 1, and then the 2 2 to get negative 1 as would be expected. So now Clifford also defined the property of a product of all n units to be omega. Omega is equal to E1, E2 to e to the n. So where omega commutes or anticommutes with each ej according as n is odd or even. Apart from scalar, omega is the only cliff of the highest grade. So in the odd case, omega is a true scalar, but in the even case, it is not. So he also went on to look at, in his paper, this is Clifford's paper, omega squared, E1, E2, En, and he squares it, and then finds that he gets negative 1 to the t, where t is equal to n minus 1 plus n minus 2, and finally, it's n, we get t is n choose 2. So in the case where S is odd, omega can be considered as an imaginary unit. However, it is not an imaginary scalar unless n is also odd. The properties of omega can be summarized in table 2. So we worked out a table and actually calculated it through and finally come to the conclusion of whether it's imaginary or real by going through and working through the formula. Okay, even subalgebras. If AB belong to VR, VS respectively, AB, okay, and we can write it out and expand it from starting in, again, matching each one and so on until we have used up everything and all the terms have grades of the same clarity. In particular, if R and S are both even, then AB contains only terms of even grade. So therefore, the units of an even grade, so we have an even grade, we have 1, EJK, EJK, LM, and then we can continue on like that, where if I is not equal to J, etc., is a closed algebra. Okay, so Clifford called this an even subalgebra. We can also extend this to odd, but due to lack of time, we're not going to do this. Okay, so a little history about vector analysis. So we have seen a brief development of Clifford algebras and what Clifford knew and did using a basis. What we now want to briefly explore is how what Gibbs knew, one of the founders of modern vector analysis, especially since I was trying to redo Clifford algebras using the language of Gibbs. So what Gibbs knew? Gibbs learned about quaternions by reading Maxwell's paper on electrodynamics. This inspired Gibbs to streamline quaternions in order to simplify calculations in physics. He did this by changing the sign of the scalar product from negative to positive, separating the dot product from the cross product. By doing this, he sacrificed associativity, but reclaimed this by founding what's called the didactic system, which again I don't have time for. And in hindsight, he noticed similarities between Grassmann's work and his own. For this reason, he became a staunch supporter of Grassmann, stressing that Grassmann's work was both more general and historically prior to Hamilton's quaternions. Gibbs did not unify Hamilton's quaternions and Grassmann's algebras as did Clifford, but merely put them side by side. Okay, and thank you very much. And any questions? Thank you. And yes.
So I have one, which
Sure.
is that if I followed you correctly, I believe you assumed that the underlying vector space, the rank 1 elements,
Right.
were that the inner product was positive definite. They also
Yeah.
had +1.
Right.
Did Clifford do that? Make that
Well,
assumption?
the thing is, I don't think Clifford, I think he did, but we didn't go, I came a point where I didn't go back into his paper enough, okay, because I was trying to really, what I was doing was I was looking at Hestenes' work. Okay, and I was looking at Hestenes' book. So I didn't go as deeply back into Clifford's actual, I had done that last year more, where I actually read Clifford's work, but when I was working on this, I was trying to derive what Hestenes had done from what I believe Clifford had done.
So now I'm curious to know historically whether...
Yeah, now I'm
Clifford
curious, so
worked in
I have the
positive
original
definite
papers
signature
and I
or
have them with me.
Thank
So
you.
if you want to look at it after, I'll be happy to download, give you copies of the papers. Any other questions? Yes, I see your hand over there.
I find it interesting the Gibbs-Maxwell connection here that they also have in developing statistical mechanics.
Yeah, it is interesting, but it was really true from what I read, okay, that Gibbs had already pretty much developed his system. And somebody told him, he had already was reading Maxwell. He didn't discover Clifford until much later. And, but that's what like Heaviside, who also had a similar issue. I sat there, okay, for about this is going to be for my next talk, when I worked with. It really takes a long time to calculate using quaternions. And I think, and I mean real quaternions, okay? And I think what happened with both Heaviside and Gibbs, when they're applying it to physics situations, they found that, boy, is this cumbersome. So they tried to streamline and make the system easier so they can calculate things in physics. So I think that was what happened, and I can understand based on my own experience fairly recently. Any other questions? Okay, thank you very much. There's one more short thing that I just want to do because of Hestenes.